Hello everybody, my name is Andy Zhu, and today I'm going to be talking about chapter 11.1, sequences. So, to talk about a sequence, we first have to define what a sequence is. A sequence can just be thought of as a list of numbers, A1, A2, A3, all the way up to AN. And then A1 is simply the first term, A2 is the second term, A3 is the third term, and in general, ANth is the nth term. Now, there are two different types of sequences, infinite and finite sequences. An infinite sequence is a sequence which just has an infinite number of terms, while a finite sequence has a finite number of terms. In general, we talk about infinite sequences much more than finite sequences, so for the remainder of the video, I'm going to be talking about infinite sequences. Now, here are two examples of sequences that are infinite. You can tell that they follow a very basic pattern, this one increasing by 1 and this one increasing by 3. So, one of the most famous sequences out there is the Fibonacci sequence, which is defined recursively as f of n equals f of n minus 1 plus f of n minus 2. Or the next term is the sum of the preceding two terms. So we start with 1, 1, and then the next one would be 2, which is the sum of the previous two, 3, sum of the previous two, 5, sum of the previous two, and so on. Now this is the general form of a sequence. Now let's talk more about general form. The general form is usually defined as an equals something, or we just say nth term, where n can be anything. So one of the most useful methods is using infinite differences. So first, to use infinite differences, we would take the difference between consecutive terms, for example, maybe the second and third term, and then we would do that for every single term, as shown here, and then we would repeat this until we get to a point where all differences are equal and non-zero. You have to remember the non-zero part. So the number of times you do this, the number of times you take the difference, is equal to the degree of the general form. Now this can be kind of confusing said in words, so I'll show an example. So we start with 2, 4, 6, 8, 10. Very basic sequence. And then we can see that the difference, we first take the difference between consecutive terms, and we see the difference is 2, 2, 2, 2, and it's all the same, which satisfies differences are equal and non-zero. So because we repeated this one time, we know that an is the form of an is in the form of an plus b, where a and b are integers. Now, to find a and b, we can simply just solve a system of linear equations. So we plug in n equals 1, we get 2, and then when we plug into here equals a plus b, and then when we plug in n equals 2 equals 4, equals 2a plus b. And solving for a and b here, we can see that a is 2 and b is 0. So the general form would just be an equals 2n. Now, here's a harder example. Let's use infinite differences on this series. 2, 4, sequence, 2, 4, 8, 14, 22. Now, first, we would take the difference between consecutive terms. We get 2, 4, 6, 8, and so on. So then now this doesn't satisfy the condition of all equal. So we do it one more time, and we get 2, 2, 2. And then this works. And we repeated this 2 times, so then we know the general form is an equals an squared plus bn plus c. And then going back and solving with a system of linear equations, we get a equals 1, b equals negative 1, and c equals 2. So the general form would be an equals n squared minus n plus 2. Now we move on to the calculus aspect of this. So because we are in Calculus BC, this is the more important aspect. So the most important thing, and the thing used most commonly, is limits. So then we can define an as a sequence, but when we define it as a function using the general form previously, we can do a lot of things that only work for functions. So we can take the limits of these. So we now define two terms, converges and diverges. So limit of n approaches infinity equals L, where L is just some value. If L is infinity or negative infinity, then it diverges. If it is not, then it converges. So basically, divergent sequence says that it will approach either infinity or negative infinity, while convergence is anything else. So here's a simple example. The limit of n approaches infinity of an. So when we do of an plus 1 over 10n plus 2, we take the limit of this, and then we can see, because when we plug in infinity, you get infinity over infinity, so we can use L'Hopital's rule, and when we do that, we take the derivative of the top and bottom, we just get 1 over 10. So we know that this one converges. Now when we look at this one, n squared over 5, it's just pretty obvious that it diverges because the top just increases boundlessly. Now because we can treat these as functions, we have a lot of limit laws. So then these limit laws assume that a, n, and bn are convergent, and they're just convergent sequences. So the first law states that the sum or difference of the two is just equal to the sum of the difference separately, which we know is to be true in regular. And then number 2 here, it's when we multiply by some value c, we can take the c out and then evaluate the limit separately, which makes sense. From here, we show that the product of two sequences, when we take a limit of that, we can split them up. And then same with the difference, or when we divide them. But when we divide them, we have to make sure that the bottom sequence, in this case bn, cannot be 0. So let me write that right here. Let me write that bn. And we have to make sure it can't be 0, or else we would be dividing by 0. And finally, a very useful one is the limit of n approaching infinity of an to the power of p. And we can take the limit and then raise that to the power of p, as long as p is greater than 0 and an is greater than 0. And then the one most commonly used is the limit of n approaching infinity of an equals 0. If the absolute value equals 0, then the limit of the actual function equals 0. So I will show an example momentarily, but now we move on to the squeeze theorem. The squeeze theorem is something we learned previously, and it's, in a sense, it's squeezing a value in between, squeezing something in between two. So let's say we have three sequences, an, bn, and cn, where an is less than or equal to bn, which is less than or equal to cn. Now, if the limit of an is equal to the limit of cn equals some value L, the limit of bn also has to be L. And this is very logical, because if this and this are equal, this has to be equal. So, in general, the most things that apply to functions apply to sequences, because we treat our sequences as functions and we can write them as so. So now I'm going to define a few terms. A monotonic sequence, if it's monotonically increasing, it means it's constantly increasing. Every term is greater than the preceding one. Or if it's monotonically decreasing, every term is less than the preceding one. Now, monotonic sequences are useful in the sense that we know which direction it's moving in. And then a bounded above basically means it has an upper bound, or an upper bound, and the upper bound is not infinity. And bounded below means it has a lower bound. And if it's bounded above or bounded below, it's convergent. A bounded sequence is something that is both bounded above and bounded below. So it would mean that there's a lower bound and an upper bound, so it has to be somewhere in this middle space. Now here are some limit examples. The first one here is the one I mentioned before. It's that we can take an absolute value. So what we do here is we have a -1 to the n over n. So there's no easy way to solve this without using absolute values. So what we do is we take the absolute value, and we know that -1 to the n, this part, it just changes the sign. So we can get rid of that. So we just limit as n approaches infinity of 1 over n. And we know this to equal 0. Now one final theorem that might appear on the AP test is that if the limit of n approaches infinity of an is L and f is continuous, then we can take f of an, and then that would just be equal to f of L. So this is kind of confusing, so we can explain this with an example. Let's have the function sine of pi over n. Now, when we want to take the limit of this. So first, we can take the limit of just inside the pi over n and equal 0. So when we do this, now we know from this final theorem that this is equal to just taking the sine of the limit inside. And when we do that, we just get sine of 0 is 0. Now some common mistakes and helpful tips are, one of the most common mistakes is mistaking a sequence for a series. I did that at the beginning of the video if you didn't hear. A series is a sum, and a sequence is a list of numbers, so we cannot make this mistake. And then another one is just computational errors, and then just messing up in arithmetic. Other than that, there's not that many common mistakes. Some helpful tips: sequences are usually pretty easy. We just have to make sure to check our work and be careful. And also, L'Hopital's is a very, very useful thing when trying to find the limits of sequences. Thank you.